Looking more specifically at the properties of the equation we wrote, the PVS conservation equation here, which can be written this way. Haynes and McIntyre, who came up with this, discovered this or showed the impermeability properties, pointed out two very important properties of this equation. None of the PVS fluxes possess a component across an isentrope, and all fluxes point strictly along isentropic surfaces. So if you have, when you say isentropic surface, it's typically between a delta theta, as we saw in the figure before, right? So within that, you have flow, the V tilde, along the isentropes, and there is no flux in and out of the isentropic surfaces, okay? The flux of PVS across isentropes cannot occur even in a full diabatic heating dissipative system. There are no source terms of PVS in this equation, with the right hand side always equating to 0 as long as the isentrope does not intercept the ground. Remember, we didn't see the isentropic map for 330K or 315K or 330K for July, because in the monsoon season that isentrope intersects the Himalayan mountain Tibetan plateau. Okay, so that's what this is saying. Even in the presence of diabatic and frictional processes, there are no source terms for this becomes 0 on the right hand side. This is what is the impermeability theorem, that the isentropic surfaces are not permeable to PVS. The additional simplification we can seek in this case is what we said before. The Rossby waves from the jet at the exit region are recurrent phenomena. So there is always diabatic heating and convection in the tropics somewhere, the ITCZ for example, and the fluxes into the western duct and the Rossby waves are always there, which means if you integrate over a certain time, like t to t plus tau of any particular quantity, then you can get kind of a composite picture which you can consider as stationary, because it's like a climatology of the region. Okay, that allows us to write some simplified equation for the conservation of the isentropic mass density, like a continuity equation in the isentropic coordinate, and we can write our PVS conservation equation together as divergence of PVS times V tilde on an isentropic surface is nearly 0, because in this case we assume that the advective flux is much greater than the diabatic production term and the dissipative term. So once the PVS is set, it's basically being advected around, and the advective flux is what dominates, as we saw in the westerly duct and the upper trough. Okay, that's what that is saying. In this case, the potential vorticity substance is basically set by the mass source, which is related to the divergence of the sigma term, which is Sm, the source of mass, which is related to the diabatic heating. So essentially the injection of vertical mass flux into the isentrope by the convection. You can set it much more idealized system this way, as a function of latitude, a source at the equator where the flux is being created, and we can assume that it's advected out and it's being lost at two latitude bands plus minus phi s, okay, at some latitude, as we will see in a minute, which is here prescribed as a delta function. Again, an error here. This should be basically phi equal the delta equal 1 at the equator and 0 at plus minus phi s, I think. But nonetheless, just look at the figure in a minute and then we'll see. Obviously the Dirac delta function integrates to 0 when you do the integration or the area in which the mass is being pumped in and taken out. So you can integrate the continuity equation, convert the area integral into the line integral with this unit vector which is perpendicular to the latitudinal circle. Okay, that's essentially equal the source term, and that has to equal minus m over 2, where from this equation we are getting that integral. What does this mean? If you look at the symmetric circulation where you have mass source m at the equator, which is diverging, so this is a symmetric case where you are saying the mass is flowing northward and southward poleward and being lost at these latitudes phi equal minus phi s and phi equal phi s. In this case, remembering the observation that the when integrated along some latitude line like phi 0, the net PVS has to be 0 because whatever is coming in is going out south. And in this case, that would mean that the PVS has to disappear somewhere in the middle, because otherwise you're not going to have a 0 net integral. So obviously this solution we discard, which means only an asymmetric solution will work, where the Hadley cell is creating a mass source for the upper level which is diverging out, but then there is a flux inward needed, so you end up with a zonally asymmetric solution which is valid for this observations. Okay, so we just have to stick to observations and say what is consistent with the observations given the way we are prescribing the mass sources and sinks. Okay, in that case, remembering again that the advective flux being much larger than the diabatic and dissipative terms, the divergence of PVS is approximately 0 on an isentrope, and we integrated the PVS from in the isentropic direction of latitude and longitude. So it's not a xyz coordinate, it's a xy isentrope coordinate, which becomes a line integral which can be written as 2 pi a cosine phi 0, which is the average latitude in the middle. So that's the radius of the Earth at that latitude, times qs v tilde. So that since it is being taken out and brought back in, we can write that integral around in this way, which has to equal 0, because that's what observations are telling us, that whatever is going north is coming back south. Okay, so the zonally symmetric solution, assuming that V tilde has a northward component everywhere, consistent with the zonally symmetric Hadley cell, described briefly in section 10.1, which we won't go back to. So for that equation to be satisfied, then PVS must vanish somewhere along latitude phi 0, as I just said. So what is the contradiction? Basically, if you look at the zonal mean meridional circulation, the Hadley cell is northward, but there is a eddy component which can do the southward transport, which is what is implied here. Okay, we'll see that in a minute. And note that everything we have done, we haven't split the terms into mean and eddies yet. That's what we will do next. Okay, in the zonally asymmetric case, if the assumption of zonal symmetry is relaxed, and supposing that the zonal average has northward component, then 11.16, the conservation equation, implies that there must be a southward PVS flux across phi 0 somewhere that balances the northward flow of PVS associated with the zonally average circulation. So you have a zonally average circulation like the Hadley cell, and then you have somehow southward PVS being brought in. This point was made by Haynes and McIntyre, and also by Charney. It also relates to the dynamic constraints relayed by Sardeshmukh and Hoskins and Plum. These are the big names, especially Hoskins. Brian Hoskins is a very big name who brought about the general idea of thinking about PVS as or potential vorticity as a tracer for its invertibility properties that we talked about in chapter 10. So looking at the zonal mean PVS meridional flux in the isentropic coordinate, it has two terms: the mean momentum transport minus the eddy flux divergence. Okay, so this is going to add up to 0. So the Hadley cell component of the zonal mean circulation is doing the mean momentum transport, and then we have the eddy fluxes we have talked about so far compensating the northward flow. So in order to conserve potential vorticity substance, the PVS that enters the tropics is balanced by the PVS that leaves the tropics. So the equations seem complicated, but I hope you are just getting the physics of it. We are saying it in many ways, but it is still the same. Just focus on the physics and relate it to what we have done before in terms of the eddy fluxes associated with the meridional circulation and the mean meridional circulation, the zonal mean meridional circulation, and how both of them act together to satisfy this potential vorticity substance impermeability theorem and so on.